Um, okay, today it is a pleasure for me to introduce Dr. Pereira. Um, he received his bachelor, master, and PhD from the Federal University of Minas Gerais, Brazil. Um, and he is currently a joint and associate professor at the Department of Mechanical and Aerospace Engineering at West Virginia University. Thank you very much, Professor Pereira, for joining us today. We are very excited about your presentation.
Thank you, Davi. Davi and I were advised by the same person, maybe 15 years separating us, right, Davi? But
Probably
yeah,
different
I
generations.
spent like my last before coming to West Virginia, I spent my last 15 years as an associate professor at UFMG, where David got his PhD from. Right, so it's my pleasure to be here in his lab. So I'm not so young as David, but I'm starting a lab right now. So I think it's a good opportunity to show what I'm doing at West Virginia University. Okay, so let me start. Let me just put my laser pointer here so I can show. You can see my laser pointer, right?
Correct.
Okay, so we're gonna talk a little bit about the contributions we are doing on autonomous field robotics. Uh, First, I'm gonna talk about a little bit about WVU. So we present you WVU. So WVU is a old university, land grant university in West Virginia, right? It has about 20,000, 29, 30,000 students, and it's in Morgantown. WVU is in the city of called Morgantown, and Morgantown is in the north of West Virginia. I'm going to show you in the map. It's a very small university town, right? Uh, WVU is our one research institution. We have a large health science system. So most of research is done in health science, medicine, and other things like that. We call ourselves mountaineers. We live in the mountains, right? So I'm gonna show you where Morgantown is, if I can. Yeah. So this is where Morgantown is. It's very close to Pennsylvania. It's south of Pittsburgh, right? It's not so far from Lehigh over here. It's about 5.5 hours, 5, 6 hours, depends on how fast you go. So everybody's invited to come to Morgantown to visit us, right? So it's a very small city. It's surrounded by mountains and lots of beautiful nature. Those are some pictures where we can go like from our university, like 10 minutes, we get to these places. It's a big lake called Cheat Lake where you go uh, for, for boating, for kayaking, have a lot of mountains and trails. So it's a nice place. So everybody's invited to come and visit.
David should not be looking at the picture of the mountain biker because he might leave, and then he'll break his collarbone again.
But okay, so we have a group of people working with robotics. We call WVU Robotics. So a growing number of faculty and students. I was hired recently to grow this group, right? We have robotics club around over 65 students. We have a REU site, an SF REU site. So right now we are running this site. We have 10 students from all over the United States working with robotics. We have close to WVU a NASA-funded robotics technology center that basically works with satellite servicing. We have some people working with robotics. This is some pictures of people recently there. Okay, one thing that WVU is proud about is about robotics competitions. So right now we work in two robotics competitions. One is University Rover Challenge. This is a capstone course in our university. So a lot of students working on that. And we are also working in this simulated competition. This is NASA SRC2 challenge, Centennial Challenge. So we are working on having gazebo robots exploring virtual moon, right? We are in the second year of the competition right now. The first year, we had the classifications. We have only 6 teams that got the prize, and WVU was one of them. Right now, we are working on having working for the finals, right? So we're working on a nicer simulator, and I hope we can submit this by the end of July. Okay, one of the prizes that people got there is this big check here is $1 million prize, was for Fast Traverse or Fast Traverse rover. It was also a Centennial Challenge, and people got money because they could move very fast and collect samples to support the sample return missions that NASA is doing on Mars right now. Okay, so those are people, faculty on robotics. So all these 4 here in the bottom are new faculties, including myself. She was Dr. Saldanha's colleague at Grasp Labs. He just joined us in January. Okay.
She gave us a talk like 2 months ago. She gave us a talk like 2 months ago too.
Okay, so you guys know her. Okay, great. Okay, so at WVU, I founded this lab that I call Field in Area Robotics Lab. Right, I founded in 2019. I came here in the end of 2018, so I found this lab. So it's a very new lab, right? Right now we only have 4 grad students, 2 PhD, 2 masters. Some are coming in the fall, and 2 undergrad. We have only 2 people graduated, 2 master students, and we have some undergrad graduated. And we have 3 major projects that I'm gonna talk a little bit about. One is on mine inspection, another one is on forestry, and another one on space exploration. So this is the link for our lab. You are welcome to click and see more details about those projects. Okay, I forgot to ask how much time I have. I planned that to be 40 minutes, 50 minutes.
Yeah, actually, 45 minutes is fine, what we talked before.
Okay.
Yeah, we
so,
are here until 12.
Okay. So we have this mine inspection project. The idea is to move inside stone mines. So like Pennsylvania, West Virginia has a lot of mines. So one of the project is we're gonna have a ground vehicle. This is the design of the vehicle. We are designing the vehicle. This has like 3 faculties, so it's a big, large project, right? So one of the faculty is designing the ground robot that's gonna go inside the mine. It will be completely autonomous, and the ground robot we're gonna carry a drone, right? The drone is gonna take off and do some mapping of the pillars of the mine. The idea is this is for safety of the miners. We need to detect over time if we have some problems on the pillar. So, for example, cracks, things like that. So we can avoid the pillar to collapse, right? So this is the design. This is the picture that those guys took like last month. So the vehicle is almost ready. And these are some maps that we can do inside the mine with a vehicle similar to that. So those maps were done without this vehicle because this is not ready yet. Okay, my part on this project is the drone part. So we're gonna talk a little bit about that. So this is what we need to do. This is the pillar that we have inside the mine. I hope you see a video with a drone here. And we are creating a map using LiDAR. So this kind of map is what we get so far. And the idea is that we're gonna get these maps frequently, say once a year, and then we compare those maps and see if we have any problems with the pillars. That's the goal of. You see that this environment is indoor, so we cannot use GPS. We need to work on SLAM or other localization approach for the drone, right? So I'm gonna show you some of the problems we're gonna have on these. So there is a question in the chat.
Yeah, I was like,
Yeah, go ahead.
oh, sorry. So typically I see a LiDAR that's the size of, that's pretty large. That's typically cannot be fitted on a drone.
Yeah,
So what is the LiDAR you were using?
we are using a L515 LiDAR from Intel, RealSense. So it's a solid state LiDAR. It's very small, right? So
I
it goes
see.
out of the drone. The field of view is also small, so we need to move a lot to get a good map. But it is very light. That's the one we are using.
I see. Sorry to interrupt.
No problem. If you have questions, just interrupt. Okay, so one thing that we have is that the drone will be tethered to the ground vehicle. We're gonna power the drone using tether. So we are developing everything: the drone, the tethering system. So we're gonna have batteries, right? So this is a mock-up in wood, but this needs to go in the vehicle. We are planning to finish this design and fabrication during this summer. We are a little bit late because of COVID, but we are getting there. So the problem is that we have this tether. We want to fly the drone, but we want the drone to charge as well. We want to have some completely or fully autonomous drone. So we need to tether the drone to the ground vehicle. We could have other solutions to power the drone, but our solution was to have a tether. So we are creating this tether right now. And we have this is a commercial tether that we tried before, but it's too heavy. So we are designing our own, right? Tethers are nice for powering, but tethers also present some problems, right? So this is something that you can see. If you don't take care of the tether, if you don't plan correctly the motion of a robot, you're gonna have tangling, right? So this video we just did with a ground robot just to show this problem, right? This robot is exploring the environment. You see it's creating a map here while it moves, right? And it's ignoring the tether. If you do that, so this is Danilo, my student, is helping the robot right now, because if you ignore the tether, simply you're gonna have tangling. It's a problem, right? And then, although you have a map, at the end, the cable is around every obstacle. Okay, so a solution that Danilo proposed, I have a picture of Danilo here, is to do motion planning, do mapping, do exploration, being aware of the tether, right? So if you do that, you can avoid tangling. So in this video, he shows that's possible to do the same task without tangling around obstacles, right? I'm gonna just show how he does that. It's kind of simple, but you need to worry about that, right? So basically what he does is he keeps tracks of the tether configuration, right? So in a situation like that, for example, this is a robot, they have an obstacle right here. He has an estimate of the tether, right? So if he has this the estimate of the tether, what he can do is that he has to go here, for example, the robot needs to go here. So you know, this is the optimal tether configuration. So you go in a straight line, right? You can do that using a path planner, for example. You can compute that. And basically what he does is he compares the current path, this one, plus the shortest path to the goal with this one. If when you compare, the difference is too large, so he decides, okay, so I cannot follow this shortest path. I need to go back and then go to the goal using another path. So I avoid tangling, right? And this new path is a path that you need to compute considering what we call, so someone is asking something here. What's the environment is not a 3D distribution of a floor plan? Yeah, so that's another problem. I'm gonna talk a little bit about that. But basically, one thing we have here is that we need to plan this path following what we call homotopic constraints. So basically, you need to follow a path that has the same homotopy of this path here. This means no tangling, right? And planning a path like that is not very simple, right? Especially in 3D. The problem with 3D is that you're gonna have, you cannot have a good definition of homotopy, right? Homotopy is very easily defined in 2D, right? So basically what homotopy is I have an obstacle here. So I have two ways to get to this point. On the right of the obstacle or on the left, right or the left of the obstacle, right? So you just, one obstacle breaks the space in two parts. So every path that goes on the right is the same, it's homotopic to each other. So if you have a lot of paths coming here, all of them are homotopic. If they go to the left, they are not homotopic to the ones that go to the right. So you have classes of path, right? So motion planner should take care of moving on a specific class, right? If you're in 3D, you cannot do that. So you need to have some like the question here from, let me see who asked that, from Jeff. Thanks, Jeff, for the question, is that you need to have this constraint. You need to have these, the environment should be a 3D extrusion of the planar floor. So to do this kind of motion planning. Of course, we are thinking on other solutions, but we need to have other mathematical tools. We cannot use homotopy. Okay, so this is an algorithm he has. Basically, it's a standard exploration approach. You select the goal, right? But then here's the difference. You need to do two computations of shortest path. One on how to go from the current position, and one how to go from the tether anchor for the initial position, right? And then here you compare both, right? If they are too large, and how you select how different the paths can be. This number L max would be in function of the geometry of the obstacle. So in function of the circumference of the obstacle, for example, right? So if this number is the circumference of the obstacle, for example, you can prove that if this condition is satisfied, you're not gonna have tangling, right? So when you find that these constraints are broken, you just need to plan. This is called shortest edge path, because this edge from homotopic. You need to plan a path that has the same homotopy of the shortest path. Another question here. Can you measure the length of the tether extent? Yes, we have a sensor for measuring that. In these implementations, yeah, and also the tether retracts. So basically, I'm not showing this in this presentation, but yeah, we have a retraction system with an encoder, and also with tension sensor. So basically, we always keep the tension of the tether controlled, and then we can measure the length of the tether. Yes. Yes, we can integrate the length of the tether in SLAM. That's what I'm gonna show in the next slide. Yeah, we can use the tether for localization, right? So basically, we can have some sensors. So we measure IMU, we measure drone acceleration, angular velocity of the drone, and we can measure the tether length and the tension using those sensors. And we can measure some angles here, azimuth and elevation angles, both in the drone and both here. So I have a lot of measurements. This is not very easy, actually. We are working hard to make this system to work, but if we can measure all of these, we can use the tether for localization, right? So basically, we can assume that the drone is moving very slowly. And if the drone is moving very slowly, you're gonna have the format of a catenary for the tether, right? So that format has very known equations. So basically, you can get the position of this point, the position of this point as equations that use the angles and all the parameters that I just measured, right? So you can do that. So more questions. What the sensor you measure the tension? We have some pulleys, and we have one moving pulley connected to a spring, and the movement of the pulley we are measuring with a potentiometer, right? So we are making a tension movement. So basically, it's using properties of the spring to measure the tension. Okay, so if we do that, we can pose estimation problem, right? So we're gonna have, for example, in our case, use a common filter, and then we have a model for the system that includes drone model and using IMU and stuff. This part is linear, and a non-linear part that has to do with the tether. So it's kind of complicated, but this can be solved, right? So using EKF, for example, it's non-linear, so see the measurement is non-linear, so I need a extended common filter, and then we can estimate the position and the velocity of the drone. For us, it's very important to estimate the velocity as well, because we're gonna do landing on the platform using this kind of system. This is a simulation. This was presented, it will be presented next week on EQUAS by my students, Rogério. And it's possible, right? We didn't test that yet in the real drone because the drone is not flying. We can localize the drone with not so bad error. We are planning to test that at the end of the summer. Okay. Another thing we need to do, because remember that we have this ground vehicle and we have this drone that needs to land on the ground vehicle to move. So basically the ground vehicle, we're gonna carry the drone around, right? So we also develop some landing strategies. So one of the landing strategies I'm showing in this video was proposed by Vinicius. Vinicius is my former student in Brazil. Now he's a fellow faculty over there as well. And we defined this method based on vector field to land, right? Right now in these videos, you're using vision to land, but the idea on the robot is that you're gonna have the tether for localization. We're also equipping the drone with UWV sensors. So if the tether doesn't work very well, we're gonna have not a sensor fusion with UWB sensors, range sensors to avoid. But this is something that we did last year for that. So in this case, we have this camera, and the drone is detecting the marks using vision. Yeah, I think I'm gonna move a little bit faster here. How it works, basically, we define the shape of the trajectory we want the drone to land, and then we define a vector field that converts the drone to this shape, right? We compare that with visual surveying. Another question, let me respond to the question. The tether is strong enough, perhaps it could guide the drone. Yes, we are planning to do that. Thanks, Jeff. Yeah, we are planning to do that. And also we are using the tether for keeping the drone on the ground vehicle while the assembly is moving, because the mine is the terrain is not very flat. So we need to keep the drone over there so the tether can help. Yeah, but we are planning to use the tether to help the drone to land. Yeah, so we define these vector fields. When you compare this approach, vector field approach, the good thing about vector field approach is that independent of where you start here, you're gonna go to the goal, right? So basically you're gonna land. So we compare that with visual surveying and trajectory following. And you see that visual surveying is very nice, but you cannot define the trajectory. It's very important for us to define the trajectory, because if you see our robot, we're gonna have some obstacles on the robot, like lidars and things like that. So we need to here have all these sensors here. So we need to avoid these guys. So basically we need to define a trajectory that avoids this. So visual survey cannot be used for that. Trajectory following is good. but when you have some disturbance, like here, we simulate that we lost some height here. What happens is the vector fields will continue landing the vehicle. Trajectory follow, we're gonna make the vehicle to go up to follow the trajectory. So sometimes this is not very good. You have some weird movement for the robot. So we like this vector field approach. Okay, next step for this project. We are currently developing a new drone, right? The drone we're using for the experiments are M100 from DJI, but we cannot buy more. This drone is out of market now, so we cannot buy another one. So I develop another one, right? We also planning to have a completely tethered powered drone. So we don't have batteries on the drone, so we can save some weight and put more sensors, for example. We're also working on having a landing gear and a deck, specialized deck that allows a robust landing. So here is a drawing of that. So we're gonna have some like ramp here. If the drones land in different positions, gonna slide and go to the center here, for example. And then we can have some locking mechanisms here. And the tether could help also, like Jeff said, to push the drone to this position, right? We need to integrate localization and landing. And we need to integrate these with ground robot and then test a lot. The idea is to have completely autonomous vehicle, like two vehicles system, right? Ground robot and drone working together, mapping the mine. This project is finishing the end of next year, so I think we have time to do all this. Okay, the second thing I'm gonna talk about is forestry. So West Virginia has 81% of the territory covered by trees, right? So a lot of people working with trees. And what problem that we have is pest invasion. So this is a bug, for example, that makes these holes on the trees, and this thing kills the tree, right? So we are developing some drones like this one that goes making a map of the trunk of the tree and trying to detect these pests, like here. So right now it's not carrying any, on this video is not carrying any special sensor, but the idea is to have like thermal cameras and things like that to detect these holes here. And then if you detect the hole, you can say, okay, this tree needs to be fixed, needs to kill these bugs here. Right, so other applications will be, okay, I need to measure those trees. I need two people to measure a tree. I could have a drone with LiDAR to measure that, right? But to do that, we need to fly the drones under the canopy of forests. That's not very easy, right? One thing that the problem we have is that we're gonna have collisions, right? Lots of collisions. So one thing that my student Al Mahmoud did, he just defended his thesis, was to create some caged drones, right? This is a drone that has a 3D gimbal inside. So you have a cage that can rotate around the drone, right? And this is like supposed to be resilient to collisions. So you can fly, for example, we can collide, you can touch it, right? We have some commercial drones that do the same, but that was his master project to try to make something that is simpler and cheaper, right? So the cage is very nice. The drone can work as a ball, can rotate in the ground, and now you're trying to explore those stuff, right? And the idea is I'm gonna fly in the forest so I can collide with everything and still fly, right? So that's something that we are researching right now. Okay, so the problem is that this drone is kind of very hard to make, right? This gimbal system, and we need to save weight because drone needs to fly, so cannot be heavy. It's kind of very, very complicated. So we propose some different cages. I don't know why it's not running. Should be a video. Okay, let me play here. It's not playing. Cannot play media. I don't know why. Yeah, but that's a different kind of drone. a cage. So this doesn't have the gimbal, so it's much simpler to create. One thing about this drone is that when it falls, it always falls in the takeoff position, right? So the idea is to have a shape of the cage in a way you have this behavior, right? So the drone is falling and then it goes to the takeoff position and then it can fly again. So this would be good for forests. Even if I collide and I fall, I can take off again, right? So this is something that I have some students working on. Okay, so in spite of that, flying in the forest is hard. We have some problems with GPS, localization, things like that. But the big problem is that we don't have a map of the forest. So we need to avoid obstacles all the time, right? So this is a research I did in Brazil some years ago with those students, Antonio and Henrique. And we show here a drone flying and avoiding obstacles. So basically this is carrying a LiDAR as well. This is a planar LiDAR. It's a Hokuyu, is not so small as the Intel one, but it can detect some trees. You see it's following some trajectories here, detecting trees and avoid. I'm gonna show you how we do this stuff. Okay, so our solution is based on two planners, right? We have a global planner. The global planner, in our case, is a vector field, right? You see that we like vector fields. But what the global planner does is it gives the drone the main direction of movement, right? But it doesn't know the obstacles, for example. It's impossible to know because trees, the environment is dynamic, we can have movement, you can have other stuff, right? We don't know the obstacles. So the vector field is just saying the direction, okay, move in this direction, follow that curve, things like that, right? Then we have a second planner that we use as a local planner. This will be an optimal planner, right? So that optimal planner has two goals. One is avoid obstacles and no-fly zones, and the other is to follow the vector field. So basically, I have a planner to follow the vector field here, but that will create paths that are free of collisions, right? And then when we have this planner is gonna send trajectories to a trajectory control. Okay, let me talk a little bit about the vector field. So again, Vinicius here, this is the vector field guy, and he developed this vector field to follow curves, right? So it's something that was published in 2010, and we are using this vector field for several tasks, and I'm gonna explain a little bit about this vector field. So basically you have a curve here, and you create a vector field that guides a point robot to this curve. We're assuming a first order linear robot, like a completely holonomic robot. It can be in any dimensions, right? But these vector fields will not control non-holonomic or any kind of other dynamic robot. So that's why we need another trajectory planar to follow this vector field with a real robot. So how this vector field works? Basically, we define the vector field or the curve the vector field you're gonna follow by the intersection of surfaces. So in 3D, you need two surfaces, right? So the intersection of these surfaces, the surfaces you see, these are dynamic surfaces, they can move, right? So defines this curve here. So basically gonna now define a vector field for this curve. So let's call each of these surface alpha. So in this case, we have alpha 1 and alpha 2, two surfaces, right? In 3D, we need two surfaces. And then we define this curve here in 3D. So the vector field is very simple. Basically, we have two components. One component solves the convergence to the curve. So we create a vector that's orthogonal to the curve. And then we have another vector field that's tangent to the curve. That will make circulation of the curve. If you combine both vector fields, you're gonna have something like that. So a point robot here, you're gonna converge and circulate the curve, right? So merging these two things. The equation for that is not as simple. In 2D is very simple, but in ND is not very simple. Basically, you're gonna define a scalar function. This scalar function will be a function, is a functional actually, because it's a function of each of these surfaces, right? In 3D, you're gonna have two surfaces here. And then the attractive term will be the gradient of this scalar function. Okay, so this will be normal to the curve. Okay, and then to circulate the curve, you're gonna have this is called wedge product. Basically, this is a cross product in n dimensions, right? So you're gonna do the cross product of the gradient of each surface, right? So the cross product, you know, that's orthogonal to each of the vectors. So orthogonal to the attractive term will be tangent to the curve. So this is normal to the curve, and this is tangent to the curve. This is attractive term. This is the circulation term. And we have another term here to compensate for the motion of the surfaces, right? So this term is very important, but not very useful for most of our tasks. So I'm not gonna spend a lot of time on this term, right? And although this is very complicated, we can implement this very simple. I mean, the equation looks complicated, but it's very simple to compute. Okay, and we have a proof that these will lead the robot, if this is a first order robot, to the curve. So we are using this field a lot, right? So once you have this field, to control the robot, since the robot is not holonomic, completely holonomic, and since this vector field is not avoiding obstacles, we need this optimal planar here. How it works, basically, optimal planar will solve an optimization problem like this, when you're gonna find the trajectory, this is the trajectory, right? And in function of optimization functional that depends on the vector field here, right? We're gonna compute this functional or solve our problem inside a finite horizon, inside a ball around the robot, in our case, right? So I'm gonna show you how to do. So how it works. Basically, this is an example of a functional that we use. This functional is in function of the derivative of the trajectory and the vector field. Derivative of the trajectory basically is a vector that is tangent to the trajectory. And this is the vector field. So this functional is saying, if the trajectory is parallel to the vector field, the cost is small. If the trajectory is orthogonal to the vector field, the cost is high. If it's anti-parallel to the vector field, this cost is higher, right? So basically, using this functional, you can see an example here. The red curve is parallel to the vector field, basically. It's following the vector field. So the cost computed by this functional of this red trajectory is smaller than the cost of this pink trajectory that goes straight here. So the straight line trajectory is shorter, but doesn't follow the vector field, right? So basically with this functional, we guarantee if you minimize this functional, the trajectory will follow the vector field, right? When you have obstacles, you have similar things. So basically here, you see, it's shorter, the pink trajectory is shorter than the red one, but the red one follows the vector field and avoid obstacles. Both avoid obstacles, of course, because motion planar, the goal is to avoid obstacles, right? So how we solve this optimization problem? We solve using RT star. RT star is a asymptotically optimal motion planar, right? So basically it finds the optimal trajectory given a functional. And in that case, we're using that functional. So you see here a robot following a corridor and avoiding obstacles, right? This is a work of my former master student in Brazil, Elias, right? And we also use that for the drone. So basically you are solving RT star on the drone as well. I'm gonna show you a video of these. Okay, sorry, let me come back. So this is Elias video on a ground robot following this strategy. So it doesn't know the position of the cones, for example, and it's basically following a vector field that's moving straight in the corridor and doesn't know the person, of course, and avoids that person just using this strategy. So it's following the vector field and avoiding obstacles. And that we use the same strategy for the forest. So this is actual data from the forest. So this is trees that are detecting Every time we detect a tree, we create a region of avoidance around the tree, and the RT star is solving this. Right? The only problem with this is that RT star is not very fast, right? So it takes about 1.5 seconds to compute this optimal trajectory here in this specific case, right? So we have a question: how fast can we go, right? So this paper points some very interesting limits for how fast can we go, especially in the forest, right? So basically, we have the dynamics and the control of the robot. If the robot can, it's not fast enough, of course, I cannot move fast, right? The nature of the obstacles, some question here. Have you thought about informed RT? Yeah, of course. Yeah, we tried other stuff, right? Informed RT star is not applicable to this problem because actually we don't know the goal at the beginning, right? And we are using RT star in anytime mode. Yeah, we are. So that's why we can choose the sampling time, right? So we can have 1 second, 1.5 second, 2 seconds. Of course, if we have more time, we can have better trajectories. Yes, we are using that. But coming back to the informed RT star, that's a good point. We don't know the goal until we compute the whole tree. Why? Because if you look at our problem, I'm coming back here just to show a problem. We don't have a goal. The goal is not defined here. So what's the goal? The goal is the point at closer to the borders of the horizon with the smallest cost. So we're not choosing the goal, right? So I cannot use informed RT because of that. Can you reuse RT star? Yes, I can reuse RT star, yes. But I'm not doing that right now. But yes, that's something that so I think you guys understood. We need to do it fast, right? Because if I plan fast, I can move fast, right? Right now I'm using on the forest 1.5 seconds. I think on the ground robot 1 second to plan, right? Using anytime properties of RT star, yes. But then I have this student, Bernardo, that proposed something different. Instead of using RT star, maybe we have something that's faster. And the idea is why RT star is not as fast? Because it needs to compute collision all the time. So I need to check collision all the time. And checking collision is very slow. Usually checking collision is about 99% of the time that we do, right? So the idea of Bernardo is instead of creating the nodes in real time, you're going to create the nodes offline. So you create a lattice like that. So the nodes are not random anymore. You're going to have some nodes, fixed nodes in a lattice, right? And then since the nodes are fixed, we can have a sensor to graph mapping. So we know for each beam of the sensor of the LiDAR, we know the nodes related to that beam. At least the edges we know, right? Not the nodes because we have more beams than nodes sometimes, but the edges we know. So when we detect a collision using a specific beam, I can just remove the edge from the graph. That's what we call pruning. So we create the graph offline and we prune the graph online, right? So pruning is much faster than creating a tree, right? So everything else we do online. So we prune the graph, we do cost assignment on the edges and then on the nodes, and then we do path optimization. This was the paper that Bernardo just presented in NICRA yesterday or the day before yesterday. Okay, so let me show you a little bit about that. So another question here. This seems similar to the notion of motion primitives. The difference here is that we have this mapping in between sensor and edges, right? So yes, we have the primitives, is kind of that. We have all the motions possible, but we know how to remove those motions very fast, right? Yeah, this is similar to motion primitives for sure. Thanks for observing that. So he has he has this approach where it's parametric, so you can choose the number of layers, trunks, and branches. So usually it's much more dense than that. The graph is much more dense than that, right? But the idea is that for each point in the space, you may have more than one node on the graph. So usually we draw this in 3D because for some positions we can have two nodes, right? So you have several trees coming from the root, right? So this is something that we have. And another thing that, because this looks like we have straight edges here, looks like we have a lot of triangles. So he creates a mesh of triangles, and then he can prune the edges by detecting collision between the laser beams and the triangles. Okay, so what he does in real time, so he has these mappings. This is a lookup table, basically. We have triangles to edges. This is a lookup table, another lookup table, laser beams to triangles. So in real time, he just check if a laser has an obstacle. If it has an obstacle, I know the triangles that are related to that collision, and then I know the edges automatically. So this is very fast, right? And he checks collisions. He increases a little bit the size of the beams to take care of the size of the robot. So it's very easy to check the collision, right? And another thing that's nice is that because we have a fixed number of edges, a fixed number of laser beams, a fixed number of triangles, you can do everything in parallel. So this makes the thing even faster, right? So he has an implementation on CUDA, and this is really, really fast. Does it take into account dynamic obstacles? No, it doesn't take into account dynamic obstacles, but because we are doing this really fast, you see, we can do in less than 10 milliseconds. Usually we can avoid dynamic obstacles. Even if you consider the dynamic obstacle as static, because you're doing very fast, if the dynamic obstacle is not extremely fast, you can avoid it, right? So that's the idea of moving fast, of computing this fast. Of course, maybe you cannot avoid it because the robot dynamics is not enough to avoid it, but at least the path will avoid something, some dynamic obstacle. The trajectory will avoid. If the robot will gonna avoid, I don't know. Okay, so after we prune the graph, we do simple BFS very fast to do cost assignment. And then we find on the leaves of the graph, we find the one with the smallest cost, and that will be our goal. And then automatically we just follow the back points and get the path, right? Of course, the path is not very smooth, but it's very close to the optimal path. It's much faster than RT stuff. This is a simulation. So the black dots here are trees. This is the vector field. This is the dashed line is the curve that we need to follow. And this is the lattice, right? So it's doing avoiding all the obstacles and following the vector field. If you see a zoom out of these, you see that it's actually following. Of course, it's not perfectly following because we can have some trees on top of the curve, right? But it follows the vector field very fast. Okay, so he did some simulations, increasing the density of the forest, and even in very dense forests, you can still follow the vector field and still can follow the curve and avoid obstacles. Of course, it's noisier here because you have more trees and you need to avoid more trees. Okay, this is some experimental results. We didn't have experiment with drone yet, but this is avoiding like a fake forest in our lab. Create robot, very slow robot. And right now it's not using CUDA because this very simple laptop doesn't have CUDA on this, right? We compare with RT star. So in the same simple laptop without CUDA, this is i3 processor, we see that our method computes this path here in about 30 milliseconds, right? If we give RT star 30 milliseconds, we're gonna have these gray paths here. They are worse than the one we computed. If we give RT star 3 seconds, it's gonna compute the optimal path here. So you see our path is not the optimal. It's not very close to the optimal, but it's good. It's a good path, right? This could be improved. If we change the shape of the lattice, this path could be closer to the optimal path here. Okay, this is not parallel implementation. With a parallel implementation, we get speed ups of 50 times here or 30 times, depends on what you do here. So in this case, he was trying this on different densities, right? So basically the density is not important if you're doing parallel, right? So you can do, it increases, the time increases when you have serial implementation, but in parallel, basically is a constant thing, right? The same thing if you change the number of triangles or the complexity of the lattice. If you increase the complexity of the lattice, you're gonna improve the path. You're gonna be closer to the optimal. And if you do in parallel, it doesn't change the time of computation. What's very good, right? So we can do in parallel, we can do very fast, see less than 10 milliseconds to compute a path, right? Remember that RT star works in orders of seconds. So this is much faster than RT. Okay, so why this is fast? Because we are pruning instead of creating the tree. Another question. So is this algorithm making use of GPU? Yes, it's using GPU. In this implementation, it doesn't need to be implemented using GPU. So yes, so this result is using GPU. This one is not using GPU. It's still very fast. See, here we have less than 80 milliseconds compared to RT star. Is still very fast, right? But it can be even faster if you do that. A better option for your problem might fast marching method. I think fast marching method is also dependent on the goal. Remember that we don't know the goal. The goal would be the optimal the node with the smallest cost given that cost function. But I agree, if we have a goal, we can have several other solutions. RT star is not the best one, right? But in our case, we don't have the goal. That's the constraint we need to work with. Okay, so it's fast because we do pruning instead of creating the search tree, right? And we can do parallelization because we have all fixed number of edges, fixed relationship between triangles and edges, and fixed number of laser beams on the sensor, right? So you see the optimal path planning less than 10 milliseconds. Of course, it depends on the computer. And that computer is much slower. It's like 5 milliseconds, right? 10 milliseconds is very fast, right? And remember that RT star takes seconds. Okay, next steps will be to fly an actual drone. So Bernardo is working on this to fly the drone in the forest. And then drone can fly very fast if you want. So that we're gonna push the drone to fly as fast as possible given that motion planning. Another thing that we are starting to work in this summer is to develop new cost functions. I'm finishing, I know I'm a little bit late, but we have a new project that's flying this vehicle on the atmosphere of Venus. This is a NASA project, right? So the problem there is that we don't have artificial vector fields. We have natural vector fields. We have winds. So how we're gonna fly this vehicle? We need a cost function that takes into account the aerodynamics of this vehicle, for example, right? That's something that we are working on right now. And that's it. Thank you. If you have more questions, feel free to ask. This is my email if you want to ask questions after this. This is social network stuff. I don't understand those stuff, but I think this is a website and this is a Twitter. Bernardo tweets, I don't tweet. Okay, thank you.
Thank you very much, Guilherme. It was a very, very interesting talk. I invite everybody to email Guilherme. The email is also in the invitation email that I sent. Do you guys have more questions? Yeah, Wangi.
All right, thank you. Very interesting work and great presentation. So I have a few questions about the mine detecting problem. And the first thing is a small possible naive suggestion. So you talk about the robust landing of the drones onto the mined ground vehicles, right?
Mm-hmm.
So yeah, you want to land in the exact position. So there is a very naive approach. You can probably detach some very strong magnets to the landing gear of the drone, and also on the platform.
Yeah, magnets are not good for drones. You know that we have magnetometers on the drone. If you put a lot of magnets, that will be a problem, right?
All right, okay. Yeah, but
Yeah,
only on the landing gear. So that'll be extremely far away from your controller on the drone. Yeah.
Yeah, I agree.
So
Yeah,
yeah, that is
that's
a
something
naive
we can
approach.
do.
So that may not work. So I also have two other questions. And first one is when we're talking about the using the tether to solve the solving the tether problem with overlapping, not overlapping, but tether problem with obstacles. So
Okay.
since we are doing the SLAM with drones in an unknown environment, so what will happen if we do not know the existence of the obstacle? For example, if we tangle with the obstacle that we do not know the existence.
Yeah.
So do you consider that situation?
Yeah, basically, we are doing that right now on these 2D problems. So we don't know the obstacles.
Mm-hmm.
We are doing exploration. See?
Yeah.
So if you don't know the obstacle, you just assume that you can go straight. Then start detecting the obstacle. See, you're creating the map right here in the left, right? And you create yes, we are considering that. So we don't know the obstacles a priori. We are doing exploration. And then we are considering the obstacles as the obstacles are discovered. Yeah.
That's
One
right.
thing that our method needs to know, it's to have a guess at least of the size of the obstacles, because we have this parameter on the algorithm, this parameter here, that's L max, and this depends on a little bit on the size of the obstacles. So on Danilo's thesis, he did some experiments and he said, okay, it doesn't depend too much, but depends a little bit. So that's what the guess we want, but we don't need to know the obstacles a priori.
Oh, right. Yeah, sure. Yeah, the one last quick question would be, do we consider when using the tangle-free the algorithm to solve that problem? So do we consider there always exists a feasible solution when there's more than one obstacles? So you mentioned that we'll go backwards with the tether and to avoid the tangle, right?
Yeah, there is always a solution actually. Because if you look, suppose you have two obstacles, right? Saying, so if you have a path, so see, this is the shortest path, tau s. If you have this path, right? The only thing you need to know is I need to plan is a path that is homotopic to this. So if there is a path, it's possible to do the homotopic path to this one. So it's always possible. So you create this age here is age star. This is the homotopy we want, right? So this is a concatenation of the homotopy of the smallest path and the homotopy of the path you are. So we can prove that this is always possible, right?
All right.
It's maybe hard to find, but it exists, right?
All right. Right. Thank you.
Yeah. So this doesn't depend on the number of obstacles actually. So if you have those two paths, this solution exists.
Okay, I think Gustavo and Mingu have more questions. Gustavo, do you want to go ahead?
Yes, thank you for your presentation, Professor Guilherme. I have two questions are related with the tethered project. And it's like, do you consider frictions in between the cable and the obstacles when the robot is turning around? And also, when the quadrotor is tethered, do you consider like the mass of the cable changing and increasing the tension in the quadrotor?
Yes, and yes. Oh, it's okay. No, actually, the algorithm, if you see here, doesn't consider anything about dynamics of the tether. So we have friction, you're right, in between the obstacle and the tether. And we are not considering explicitly, but we notice that with our algorithm, we're not gonna have friction, or we're gonna have less friction. You see here, for example, in this video, because you are in every time you're trying to avoid this, so yeah, you have friction here, but then it gives up and go back, right? So you have some friction, but we don't need to consider basically, right? At least in our experiments, we didn't see any problem with that, but that could be a good thing to investigate in the future. If you look at the other solution without the algorithm, where you ignore the tether, see what you have. In this case, friction is a big problem, see? And that's why you see Danilo running here sometime to help the robot. Because if you don't help the robot, friction will prevent the robot to push the tether, right? So basically, by avoiding tangling, you also help in this matter, right? And the other question was on the drone problem. Are we considering the mass? We are not considering the mass explicitly as well, but we have a sensor that measures the tension. So indirectly, we are considering the mass, right? But we don't need to consider that on our equations because the tension will take care of these as well. Tension basically is the force, and mass is being considered in this force, right? But thank you for the questions.
Do you want to continue, Mingo?
Yes. Hi, Professor. They are
Hey.
very practical projects and very impressive. And I just have two primary problems. For my exploration, it seems that the cave has enough space, like we can allow the drone to fly. So what's the benefits compared with the human beings? It seems that we can drive it directly into the cave. So in this situation.
Oh, yeah. So that's a problem. I should have some other pictures here. This mine is huge, right? So basically, this mine covers like it's larger than our city here. It's underground and it's large. So you could have people, but that would take a long time to do all this. So the idea is to do some automation on that. Also, some parts of the mine, they are not being used anymore. So the old part, so it's kind of dangerous for people to go there. You could have some rocks around. So the idea is to make it safer and faster,
Okay.
right?
I see.
Yeah, you're right. It's a lot of space, so we could fly. This is kind of high. Some parts of the mine are like 15 meters high as well. It's kind of very boring for a person to drive to fly this drone over there and make these. So that's
Okay.
we want to automate, right? Not the sponsor wants to automate. This is a foundation that is actually in Pennsylvania, the foundation. And this mine is also in Pennsylvania. We are like 15 minutes from Pennsylvania here. So all these are in Pennsylvania, but they want to automate that because it's kind of very dangerous if you don't look at the pillars, and it's also very boring to do.
Okay. Yeah, thank you. And my second question is that what's the benefits of using the tethers for the mobile robot? Because I'm not that area, so I don't know what's the benefits.
Benefits basically is power, right? So
Okay.
I can have infinite power if I have the tether. And
Okay.
in our case, for the mine project, this ground robot is very big and it's very heavy. So it's gonna carry a whole set of batteries just for the drone. So instead of having the batteries on the drone, I'm gonna have the batteries on the ground vehicle, right? So in our case, we estimate that we can run about 12 hours. We can fly about 12 hours. Normally we could fly 20 minutes. So it's a good improvement of
Okay, I see.
endurance if we have the batteries on the,
Okay.
we have the tether on the drone.
Okay. Yeah, thank you. Yeah, thank you.
You're welcome.
Great.
Guilherme, I have a question. Like, since your background is in control, how has been like that transition from control? And we know some of your papers in control to field robotics. Like, that's not that common.
Yeah, actually, I like to do robots, right? I like to make the robots and solve nice problems. So the the hard part is not to use what I know on these robots. The hard part is to publish papers with those robots, right? Because you need to have some contributions, scientific contributions of that. So what I'm doing is basically I try to push to my side to make some science on the robots and work with partners, right? I have some good guys, good colleagues that like to make robots as well. So mechanical engineers, aerospace engineers. I'm electrical engineer, so I cannot design mechanically this kind of robot, right? I'm electrical engineer and with PhD in computer science. So my place is not making the robots, but I have some very good partners and very good students actually. At WVU, I'm in the Department of Mechanical Aerospace, and the students are very hands-on. So they like to do this kind of stuff. So I'm trying to use that ability to solve my problems, right? So that's the thing. But as I said, the hard part is to publish, right? Because you need to find good science on solving these problems, right? Sometimes for scientific contributions, the problems are trivial, right? So we need to invent a little bit, right? So for example, landing with the tether, things like that. So maybe we have some science on that, on control problems, some uh, landing problems, some estimation problems, right? Things like that. Of course, I could solve in different ways and to avoid those problems, but we need problems, right? To do some science.
That's correct. Yeah. Yeah, that's what we talk here. Like, more than doing uh, robots and prototypes, what we do is like experiments that show that the theory is correct, right?
Yeah.
Yeah, it's not the other way.
Depends on the sponsor. They don't care about the science. They want to solve the problem, right? And those are examples. So we need to solve the problem, and the students need to do PhDs and masters theses, right? So we still need to have the science. Cannot avoid that, right?
Correct.
But so, for example, I my PhD was in multi-robot coordination, and now I'm working with two robots. It's a coordination, but it's much simpler, right? But we need to live like that.
Yes, that's true. Okay, I think this has been very interesting. We definitely should chat more. We also have some work with cables that maybe we can find a very interesting intersection.
Yeah, that would be good.
And yeah, we definitely chat more. And thank you again, Guilherme, for the for coming virtually to Lehigh. We hope to invite you in person soon.
Yeah, I hope so. I hope so. I can come, and you guys can come here as well. If you're coming to vacations close to WVU, just let me know. You can visit our labs and see whatever. And I hope you can come to visit officially as well to do a presentation. We have some like you have in your lab, like some presentations. So I'm gonna plan for you guys to come here as well. Thank you very much for the
I
opportunity.
think we have one last question from Disha. What would you be the
Okay, let
COVID
me read it
protocol?
here. Okay, sorry. Hey,
Oh,
Disha.
is this a question for us or for Guilherme, Disha?
Yeah, sorry, it's for us, like for the lab.
Okay.
Right.
Oh, okay. We still need to update that. Right now, we didn't update the policies. We need to discuss more about that with Jeff
Yeah.
and organize.
Over here, we are already working like normally. No problem. You can go there all the time. So I think you're gonna improve. Gonna
Yeah, The thing is like right now we
policy.
have some protocols and like maximum number of people in the lab, and I think that needs to be changed.
Yeah.
It's just a few people. It's a big lab and only like 3 people can be there.
Oh, okay.
Yeah.
Yeah, we need to update that the soon because students are coming in for the summer. I think 3 people at that time would probably be a bottleneck.
Yep, that's true. Okay. So thank you very much and see you soon. See you everybody.
Okay. Thank you,
Take care.
guys.
Thank you.
Good weekend.
Thank you. Guilherme.
Thank
Okay,
you.
guys.
Bye.